I spent decades staring at equations that all pointed to the same uncomfortable truth. Time has a direction. It flows forward, always forward, never back. And for most of my career, I couldn't tell you why. The universe doesn't care about our sense of forward and backward. Newton's laws work perfectly well in reverse. If you filmed a planet orbiting a star and played the film backwards, every equation would still hold. The same is true for Einstein's relativity, for quantum mechanics at the particle level. The fundamental laws of physics are time-symmetric. They don't distinguish between past and future. And yet, drop a cup, it shatters. The pieces never reassemble themselves and leap back into your hand. You remember yesterday, but not tomorrow. Eggs scramble, but never unscramble. Stars burn out. People age. The universe expands. Everything moves in one direction through time. I remember sitting in my office at Cambridge in 1974, 27 years old, already in a wheelchair, working through the mathematics of black holes. I'd just discovered something that would later be called Hawking radiation. Black holes aren't completely black. They emit particles, they evaporate, slowly, impossibly slowly, but they die. And that's when the real problem hit me. Not just that black holes evaporate, but what happens to all the information that fell into them. Because if information is truly destroyed, if the past can be completely erased, then time's arrow becomes even more mysterious. The universe would be fundamentally losing its memory. The question haunted me. Why does time have a direction at all? Let me show you why this isn't just philosophical navel-gazing. It's the deepest question in physics. Every physical process you've ever witnessed obeys something called the second law of thermodynamics. Entropy increases. Disorder grows. That's not a tendency. It's an absolute law. Heat flows from hot objects to cold ones, never the reverse. Gas expands to fill a room. Coffee and milk mix. Mountains erode. The technical definition? Entropy is a measure of disorder, of the number of ways you can arrange a system's components while keeping its overall appearance the same. A broken cup has more entropy than an intact one because there are vastly more ways to arrange broken pieces than there are ways to assemble a perfect cup. The second law says entropy in a closed system always increases or stays the same, never decreases. And here's the key. Entropy increase is the only fundamental law of physics that distinguishes past from future. It's the only thing that gives time its arrow. But why? Why does entropy increase? The other laws of physics are reversible. Particle interactions work the same forward and backward. So where does this one-way street come from? I spent years thinking I had to find some deep physical principle that explained it. Some hidden mechanism in the quantum realm. Some feature of space-time itself that enforced the direction. Something profound and complicated. I was wrong. The answer is simpler and stranger than I'd imagined. It comes from probability and the way the universe began. Imagine a box with a partition down the middle. On one side, you have all the air molecules. On the other side, nothing. You remove the partition. What happens? The air spreads out to fill both sides of the box. Every molecule bounces around randomly, and within seconds, they're distributed evenly throughout the entire space. Now run it backward in your mind. Could all those molecules bouncing randomly, spontaneously return to one half of the box? Technically, yes. There's no law of physics preventing it. Every collision is perfectly reversible. If you could precisely reverse every particle's velocity at once, they'd retrace their paths back to their starting positions. But here's the thing. They won't. Not because they can't. Because they almost certainly won't. The number of ways to arrange all those molecules in just half the box is fantastically smaller than the number of ways to arrange them throughout the whole box. By a factor so large, it makes astronomical numbers look tiny. If you sat and watched that box for a time period longer than the current age of the universe, billions upon billions of years, you still wouldn't see all the molecules spontaneously compress back into one half. The probability is that small, not impossible, just breathtakingly unlikely. And that's it. That's the secret. Entropy increases not because of a fundamental law that prohibits decrease. It increases because low-entropy states are rare and high-entropy states are common. The universe isn't enforcing a direction. It's just following probabilities. Time has an arrow because we started in an incredibly unlikely low-entropy state. Here's where it gets strange. If the universe obeys time-symmetric laws and entropy increase is just about probability, then the far future should look exactly like the far past. High entropy in both directions, maximum disorder at both ends, but it doesn't. The early universe, 13.8 billion years ago at the Big Bang, was in an extraordinarily low-entropy state. Everything was smooth, uniform, almost perfectly organized, a tiny, hot, dense point of incredible order. That shouldn't be. If we're just following probability, the Big Bang should have been maximum chaos. The universe should have started with high entropy and stayed there. Instead, it started with remarkably low entropy and has been increasing ever since. Why? This is the real question. Not why entropy increases. That's just statistics. But why the universe began with such low entropy in the first place? I don't have a complete answer. Neither does anyone else. But I spent decades developing what I think is the right approach. In 1983, I worked with Jim Hartle on something we called the no-boundary proposal. It's a way of describing the origin of the universe using quantum mechanics and general relativity together. In this picture, the universe doesn't have a beginning in the traditional sense. At the very earliest moments, time itself becomes something different. The distinction between time and space blurs. Asking what came before the Big Bang becomes like asking what's north of the North Pole. The question has no meaning because before doesn't exist. And in that timeless quantum state, the universe's wave function naturally evolves toward a low-entropy configuration when classical time emerges. The universe didn't start with low entropy by accident or divine intervention. It started that way because the quantum laws governing the earliest moments, when space-time itself was just probability, favor those configurations. It's not a complete picture. The mathematics is ferociously difficult, and there are competing proposals. Roger Penrose has a different idea involving conformal cyclic cosmology. Others suggest eternal inflation creates countless bubble universes, each with its own arrow of time determined by local conditions. But here's what I'm confident about. Time's arrow isn't built into the fundamental laws of particle physics or relativity. It emerges from cosmology, from the way the universe began. The direction of time is a consequence of initial conditions, not a law of nature. Let me make this concrete. Right now, in your brain, memories form because entropy increases. When you remember something, you're accessing a low-entropy record created in the past. Your neurons are configured in a specific way that encodes information about previous states. You can't remember the future because the future is higher entropy. The configuration of your neurons right now doesn't yet contain information about what's coming. It contains information about what was, but imagine, pure thought experiment, that entropy were decreasing instead of increasing. You'd still experience an arrow of time. You'd still perceive cause and effect, memory and anticipation, But you'd remember what we call the future and be unable to recall what we call the past. Your entire experience of causation would be reversed. The direction wouldn't change, just which end you call past. This tells us something profound. Our subjective experience of time's flow, our sense of moving from past to future, is tied to entropy increase. We are entropic beings. Our consciousness, our memories, our sense of causation, all of it depends on the second law. In 1985, I made a bet with Kip Thorne and John Preskill about whether information could be destroyed in black holes. I argued it could be. If black holes evaporate completely and information is lost, that would be another arrow of time, a fundamental one that doesn't come from entropy or initial conditions. I lost that bet, conceded it in 2004. The information isn't destroyed. It's preserved in the radiation, encoded in ways we're still working out. Black hole evaporation doesn't create a new arrow of time. It follows the same thermodynamic arrow everything else does. But working through that problem taught me something crucial. Every arrow of time we've discovered, thermodynamic, electromagnetic, quantum measurement, cosmological expansion, all of them point the same direction. They're aligned, and they're all consequences of the same fact. The universe began in a low entropy state and has been evolving toward higher entropy ever since. People ask me, will the arrow reverse? Will entropy start decreasing again? No, the universe is expanding, stars are burning out, black holes are evaporating. Everything is moving toward what we call heat death, a state of maximum entropy where no useful work can be done, where every region has the same temperature, where nothing interesting can happen. In that far future, trillions upon trillions of years from now, there won't be any arrow of time. Not because time stops, but because there won't be any processes left that distinguish past from future. No entropy gradients, no structure, just quantum fluctuations in an empty void. The arrow of time isn't permanent. It's a feature of our era, our epoch, the period between the low-entropy Big Bang and the high-entropy heat death. We exist in the middle, in the interesting part, where entropy is still increasing, where stars still shine, where life can use energy gradients to build complexity, where memories can form and consciousness can emerge. Time's arrow is temporary, cosmically temporary, but it's what makes us possible. Here's what I realized sitting in that office in Cambridge, years after starting this investigation. The question, why does time have a direction? And the question, why do we exist? Turn out to be the same question. We are configurations of matter that use entropy increase to process information, to remember, to think, to act. We couldn't exist in a high-entropy universe. We need the low-entropy past, the organized energy from the sun, the chemical gradients in our cells, the structured information in DNA. The arrow of time isn't just something we observe. It's something we are. And that arrow points back to the beginning, to the Big Bang, to that mysterious low-entropy initial state that made everything possible. I spent my career trying to understand that beginning. The moment when time itself emerged from quantum probability, when the first tick of the cosmic clock started the countdown toward maximum entropy. I worked through the mathematics until my fingers couldn't operate a keyboard anymore, until I needed a computer system to speak for me, until my body had deteriorated to the point where the simplest physical movements were impossible. My body followed the second law just like everything else. Entropy increased, order broke down, energy gradients dissipated, but my mind kept working, kept following the mathematics forward, kept asking why. Because understanding why time has a direction means understanding why the universe exists at all, why there's something rather than nothing, why there's order rather than chaos, why there's us. The answer, I think, lies in the quantum nature of the earliest moments, in the way probability becomes reality, in the way timeless mathematical laws give rise to time itself. It's not a prison sentence, this one-way journey from low entropy to high. It's not a limitation. It's the gift that makes complexity possible, makes stars possible, makes life possible, makes consciousness possible, makes physics possible, makes questions possible. The universe could have started with maximum entropy, could have been featureless chaos from the beginning. Nothing interesting would ever have happened. No structures would form. No one would be around to ask why. Instead, we got this: a universe that started with extraordinary order and has been spending it ever since, creating stars, creating planets, creating life, creating minds that can look back and ask, why does time have a direction? The arrow of time is the most fundamental asymmetry in nature, and it's also the most generous one. It gave us past and future, memory and possibility, cause and effect, story and meaning. I meant it. Still do. When you look up at the night sky tonight, you're looking backward in time. The light from distant stars has taken years, centuries, millennia to reach you. You're seeing the past directly, written in photons, but you can't see the future. Not because of a limitation in your eyes or your instruments, because the future doesn't exist yet. It hasn't been written. Entropy hasn't increased there yet. The arrow hasn't reached it. We live at the moving boundary between what was and what will be, riding the arrow of time forward, always forward, not because we have to, because the universe began.